In topic 7, we talked a little bit about natural and unnatural radioactive decay. We looked at a couple different types of natural radioactive decay, alpha, beta, and gamma decay, and then we looked at some ways where we can get decay series to occur in a lab by shooting neutrons or other particles at larger atoms. Here we're going to look at an additional type of decay and also look a little bit more at half-lives and a little bit more deeply into natural radioactive decay. So previously we talked about beta decay, and this is when a neutron inside of an atomic nucleus decays into a proton, an electron, and an antineutrino. And so when that occurs, the Z, the atomic number of the atom, increases by 1, but the mass number of the atom stays the same because we have the same number of particles. We just have one less neutron, one more proton. And in this decay, because we've talked about previously that the mass of the proton and the neutron are slightly different, there has to be that conservation of mass, conservation of energy. And so to maintain the mass and the energy, we have the creation of an electron and an antineutrino. If the neutron is flying around outside of the nucleus, the half-life of that free neutron is about 11 minutes before it decays according to the equation that you see there. Now a related type of decay, and this beta decay as we've talked about previously, but a related type of decay is what we call beta plus decay or positron emission. And in positron emission, a proton inside the nucleus is turned into a neutron and is accompanied by the emission of a positron and a neutrino. And so these two decays are very similar. One, we have a neutron decaying into a proton. The other, we have a proton decaying into a neutron. And in the reverse equation, the proton decaying into a neutron, we have antiparticles being created. We have the positron, which is the electron's antiparticle, and a neutrino, which is the antiparticle to the antineutrino. And again, those particular particles are created in order to conserve mass, energy, and additionally charge. You'll notice in the beta decay, the charge beforehand is 0 because it's a neutron. The total charge after is also 0 because we have a proton and an electron. In positron emission, we start with a positive charge in the proton, but we're generating a neutron, and notice that it's a positron that's being generated which has a positive charge, and so we're maintaining charge through both of these decays as well. And so we can kind of look at these two equations and compare, and here we have our neutron, our proton, our electron with a -1 charge, 0 mass, and our antineutrino, 0 charge, 0 mass. And again, here's our mass is a mass of 1, a mass of 1, 0, 0, so those balance out. Same thing over here, mass of 1 and mass of 1. They balance each other out. Here's that positive charge that the positron has to balance out the positive charge in the proton. Our neutrino, much like our antineutrino, has 0 charge, 0 mass. But one of the big differences between the two is that a free proton cannot decay. Okay, so a free neutron can decay similar to one that's in the nucleus, but a free proton cannot undergo this process. It cannot undergo this decay because, and again remember, it has to do with this conservation of mass. The rest mass of the neutron is larger than the rest mass of the proton. And even if we have our neutrino that has 0 mass, our electron's going to have basically 0 mass, but that would say, okay, we're gaining mass, which we know is impossible. But that mass difference is actually made up in the binding energy of the nucleus. And so that some of that extra binding energy gets converted into mass to make up the difference between the proton and the neutron. And so that's why you're not going to see this positron emission occur outside of a nucleus. And be careful with these when we consider what's actually going on. Okay, it's not the splitting up of a neutron into a proton, an electron, and an antineutrino. A neutron is not made up of a proton, an electron, and an antineutrino. A proton is not made up of a neutron, a positron, and a neutrino. It's not breaking up into those parts like an atom splitting. The neutron or the proton that you start with is disappearing, and in its place are being created 3 new particles. Okay, so it's the disappearance of one particle, the appearance of 3 new. It's not that one being split apart. So be careful, it's a little bit different from how we view chemical reactions and chemical equations where something is breaking up and rejoining. Here, the original particle is completely going away, and we're reforming 3 new particles. Now, the existence of this third particle, this neutrino, is actually kind of interesting because it has no mass, it has no charge, and so it was very, very difficult to detect, and really if you weren't looking for it, you'd probably never find it. But prior to its discovery, it was actually hypothesized to exist. Enrico Fermi and Wolfgang Pauli in 1933 predicted that there must be some third particle being produced in this decay. And the reason for this is that if it was just the electron and the proton that were being produced in the decay of a neutron, then since the electron is the much lighter of the two, it's going to carry most of the energy away as kinetic energy. It's going to move away much faster. And so the kinetic energy of the electrons, if you work through the calculations, should be about 0.783 mega electron volts. Experimentally, though, they discovered that there was a range of energies from 0 all the way up to 0.783 mega electron volts. So there was this range, this what we call a beta spectrum range of energy that the electron actually had. And so if it was less than that 0.783, that means that there must be missing energy somewhere, and the question was, where did that energy go? What happened to it? And that's what led to the prediction of this third particle. There must be something else taking that energy, and Enrico Fermi actually coined the phrase neutrino, which is Italian, and it means little neutral one, because there was no charge and it was very, very small, actually massless. We just looked at a specific decay series, that of the beta plus or the positron decay. The other 2 major types of decay that we talked about last time were that alpha decay and gamma decay. And those 2 types of decay are also the major pieces of experimental data in support of energy levels in the nucleus. And so we've talked about electron energy levels, but there are also energy levels related to the nucleus. And as we said, that these decay series are the major piece of support for that. And the reasons for this is that as we look at those particles or emissions, the alpha particles and the gamma rays, the gamma photons that are emitted, they have discrete amounts of energy. There's not a broad range of energies of alpha particles. There's not a broad range of energized photons that are emitted in gamma decay. They have very discrete amounts. And so we can actually diagram, similar to our diagrams for electron energy levels, we can create diagrams for nuclear energy levels based on these different decays. And so looking here on the y-axis, we have energy in mega electron volts, and as we undergo different decays from bismuth to polonium down to lead, we're going from initially beta decay and then alpha decay, and you can see there are specific amounts of energy that are being released from the nucleus, and so the energy level of the nucleus is changing, and the difference in the energy levels is equal to the amount of energy that's in the particles that are released. And so as it undergoes radioactive decay, we can calculate and predict the energies in the nuclei. And if we take a closer look at those decays, we again have previously talked briefly about radioactive decay and the mathematical relationship, but now let's take a deeper look at it. The radioactive decay law actually states that the number of nuclei that will decay per second is proportional to the number of atoms present that have not yet decayed. What this means is that the more undecayed atoms there are, the greater the rate of decay. And so if we have twice as many undecayed nuclei, the rate of decay is going to be twice as great. The fewer undecayed atoms, the slower the rate of decay. And mathematically, we can express it in this form. And in this equation, the lambda is no longer wavelength, but it's actually a constant that we call the decay constant. And it represents the probability of decay per unit time. And so if we integrate that previous equation and we call the original number of nuclei n sub 0, the number of nuclei at time 0, we get n, which is the number of nuclei at that given time, equal to n0 e to the negative lambda t. And so you can see the number of nuclei at any given time is a function of how many you start with and how long after you start you're measuring. As you can see from that equation, as time goes on, the number of decaying nuclei decreases exponentially. And now if after some specific amount of time, we can call it t subscript 1/2, the number of nuclei is half as many as it was. So in this case, n is equal to n sub 0 divided by 2, half of the original number. If we do a little derivation, we can say n sub 0 e to the negative lambda t is equal to n0 over 2. And again, noticing here that we've incorporated t to the 1/2, so that's going to be our time. Now we can cross out and we get 1/2 equals e to the negative lambda t to the 1/2. If we use logs, we take the natural log of both sides, we end up with the natural log of 1/2 is equal to negative lambda t to the 1/2. We can then expand this component here to natural log 1 minus natural log 2 equals negative lambda t 1/2. And so when we simplify this and we have our negative over here, what we end up with is natural log 2 equals lambda t 1/2. And a little bit of rearrangement, we're going to divide both sides by the decay constant. T subscript 1/2 is equal to natural log of 2 divided by the decay constant. This t to the 1/2 is what we call the half-life of a particle, of a nuclei. And looking at this, you might say, well, if lambda is a constant, then everything has the same half-life. But what you need to realize is that this decay constant, this lambda, is constant for a given nucleus, for a specific type of nucleus. So no two types of nuclei have the same decay constant. So uranium-235 is going to have some specific decay constant. Polonium-240 is going to have a different decay constant. So that's why everything has a different half-life. And if we just kind of calculate this out, half-life is actually roughly equivalent to 0.693 divided by the decay constant for that particular element. Now this also means that we can have an equivalent formula for the decay equation, and in this the number of particles at a given time is again equal to the number that you start with times 1/2 to the t over half-life. So the time at time t divided by the half-life of that particular nucleus. And another mathematical relationship we have here is what we call the activity. And the activity is simply the number of decays per second. So it's kind of like the rate of decay. And because the rate of decay is based on the number of nuclei, the activity for a sample of material is constantly changing as well. As the number of nuclei decrease, the activity is also decreasing. And so if we say that the initial activity, or A sub 0, is equal to the original number of nuclei times the decay constant, and we can calculate the activity at some given time with our equation here. Activity is equal to the original number of nuclei times the decay constant times e to the negative lambda t.